Okay, hello, hopefully a quick video on the parameterization of conic sections. We did in class the parameterization of the ellipse and parabola, but taking a problem like this, x equals 5 secant t, y equals 3 tan t, from the worksheet, this was number 3, we didn't quite have a chance to do this in most classes. Alright, this is pretty hard. You might already have a good guess about what kind of conic this is, but let's take it seriously and do it properly. So first of all, I want to look at restrictions, and there are all kinds of restrictions on secant. Like I can't take the secant of pi over 2, I can't take the secant of negative pi over 2, etc. And I have similar restrictions on tan. I can't take the tan of pi over 2, I can't take the tan of negative pi over 2. So there's so much happening that I think we need to take a look at the secant function and the tan function. So when things get hard, what we can do is make a sort of side graph to help us of what 5 secant looks like. And so I'm going to put t on the horizontal axis and kind of like x on the vertical axis. And then just below, I will do something similar. I'm going to make a graph of y versus t. And this will help remind me like what the period of these functions are, what their end behavior is, and stuff like that. Alright, so let's do it. I don't know how well you guys know this. I know it's all very well, so I will just graph 5 secant. I just know pretty much by heart that secant has vertical asymptotes at negative pi over 2 and pi over 2, and also at 3 pi over 2. So that's that. And the function itself looks kind of like this, and that's like normal secant, but because it's been stretched out by a factor of 5, then if you plug in, you can always just plug in some numbers, right? Secant of 0, cosine of 0 is 1, so secant of 0 is also 1, so that's 5, and this is pi comma negative 5. Alright, that is a picture of secant. Well, just underneath, we can make a picture of the tan function. Well, the tan function also has asymptotes at pi over 2, negative pi over 2, pi over 2, 3 pi over 2, etc. What does tan look like? Kind of looks like this. Shopump and shopump. And yeah, that's probably good enough. No, maybe that's not good enough. Normally when I plug in pi over 4, I get back 1, but since this is 3 tan, when I plug in pi over 4, I get back 3. So I get this point pi over 4 comma 3, and here I have a point negative pi over 4, negative 3, and like maybe these points I care about too. That would be, that's like pi, so that's 5 pi over 4, and this is 3 pi over 4. So 3 pi over 4, negative 3, and 5 pi over 4, 3. Alright, so that's just like basic pre-calc, knowing what the secant and tan functions look like. And it is after looking at these functions that I'm ready to say, oh, okay, the period of the secant function is 2 pi, and the period of the tan function is pi. And so if the x-coordinate is repeating every 2 pi, but the y-coordinate is repeating every pi, that means the whole shape is going to repeat every 2 pi. And I can choose to graph this repeating on any interval I want, but I'm just going to choose to graph the curve on the interval from negative pi over 2 to 3 pi over 2. That's just because that's how I've graphed my x versus t and y versus t curves. And that's just because I normally think of secant as starting in negative pi over 2, even though it's periodic, so it goes on forever. Alright, having done that, then what are my restrictions? Well, my restrictions are basically this blows up at pi over 2, and also at negative pi over 2 and 3 pi over 2. So, okay, so t can't be pi over 2. And it also gets kind of crazy near negative pi over 2 and near 3 pi over 2. Alright, so to do this problem truly properly, we need to, oh, and I guess I could also say the restrictions on x, right? X is always going to be less than or equal to -5, or X is going to be greater than or equal to 5, because that's how secant works, and there are no restrictions on Y. Okay, now we have to do the end behavior step. Well, there's no end behavior because these functions are periodic, but there is like craziness. And where does the craziness happen? It happens when X or Y gets really huge. And when does X or Y get really huge? At pi over 2, negative pi over 2, 3 pi over 2, etc. So if we want to be very careful about this, we need to look at what happens as t approaches negative pi over 2 plus. In other words, when I'm a little bit more than negative pi over 2, what's going on? And then we are also going to investigate what happens as t approaches pi over 2 minus, and then also what happens as t approaches pi over 2 plus, and what happens as t approaches 3 pi over 2 minus. These are the 4 t values where things get kind of crazy, and it's particularly helpful to have the graphs right here. So then this makes this basically just easy because you can just look at your graphs. So what's happening a little bit more than negative pi over 2, X is going to infinity, Y is going to negative infinity. What's happening as t is approaching pi over 2 minus, well, if I'm a little bit less than pi over 2, X is going to infinity and Y is going to infinity. And as t approaches pi over 2 plus, X is going to negative infinity, Y is going to negative infinity, just reading this right off my picture. And as t approaches 3 pi over 2 minus, X is going to negative infinity, Y is going to infinity. Okay. All of that is like getting ready to almost like kind of start doing the problem. And what we need to do now is, I'm gonna zoom out a little bit, is like eliminate the parameter and then like make the graph. Well, should be enough room. How can I eliminate the parameter? Well, we can see that secant and tan are related. It's just a fact that tan squared theta plus 1 is secant squared theta. And therefore, I can solve for secant t. Secant t is x over 5, and tan t is y over 3. And so the sort of trick to eliminating the parameter is to see this sort of trigonometric relationship, this Pythagorean relationship. Okay, so basically what do we get? We get y over 3 squared plus 1 equals x over 5 squared. And so, big surprise, this is a hyperbola. What kind of hyperbola is it? If I move that over, this is going to be x squared over 25 minus y squared over 9 equals 1 hyperbola. Okay, and some people just went immediately to that, but I really feel like it's important to do all that other work first. And all that's going to be going into the graph. Okay, let's now make an annotated sketch of what's really going on. What is going on? Well, this is a horizontal hyperbola. So 2, 3, 4, 5. 1, 2, 3, 4, 5. The vertices are going to be here and here. The y coordinate has been stretched out by a factor of 3. So we got a little bit of this and a little bit of that. And then making the happy box and the diagonals of the happy box, and I will now, I don't know why I put dots there, I will now make the hyperbola itself, which is going to come in like this. Alright, so that's kind of that's like part of the problem down. This is the path, this is the shape that the parametric curve it makes, but I want to know how it happens as well. So I want to annotate the figure. So okay, let's go through. Oh, we can also plug in some. Well, let's just start. So at time negative pi over 2 plus, which is the beginning of my interval of width 2 pi, where am I? Well, x is infinity, y is negative infinity. So I'm at like infinity comma negative infinity. So that suggests that I'm here at times t equals negative pi over 2 plus. Yeah. And that means, well, what is x doing? X is getting becoming smaller, and y is becoming a sort of less negative. And so x is getting smaller, y is becoming less negative, and eventually we hit this point. Well, when do we hit that point? When t is 0. If you just plug in 0 for t, you can see that x is 5 and y is 0. So this is the point 5 comma 0, and this happens when t equals 0. So it's all like making sense. And then you do a little bit of this, a little bit of this, and then consulting my chart, it did this one. What comes next? As t approaches pi over 2 minus, I'm at infinity comma infinity. All right, so then this is t equals pi over 2 minus. And basically what happens there is teleportation. And so we teleport to, where do we teleport to? We teleport to the pi over 2 plus location, which is negative infinity, so that's down here. So we get t equals pi over 2 plus, and I'll draw in the teleporter, oops, just done it in green for color coding purposes, but basically, yeah, this is like A. So I teleport from here down to there, and then up, and then I guess it's at when t is pi, x is negative 5, y is 0. And that's exactly what we have here. So it's all making sense. This is t equals pi, and then finally, as t approaches 3 pi over 2 minus, I'm at negative infinity comma infinity. But it doesn't quite stop there. Of course, the curve is periodic and repeats every 2 pi. So I'm going to teleport from here to the beginning back again. And so and have another teleportation from here to here. And that is the sort of order in which this whole hyperbola is made. Okay, good. Hopefully 12 minutes, pretty reasonable. Hopefully you get it. And then there's another problem on the next page that's basically the same thing but a little bit harder. Okay, bye.